Hello everyone, welcome. I will start an assessment first of all before introducing myself. The first question is from 1 to 3, how was the coffee? Satisfied? Too satisfied, oh my god. Very satisfied? Another one. Extremely satisfied? Oh gosh. Okay, so the second question for the assessment was how many of you ever worked with Kubernetes? Okay. With Azure? Cloud computing? Distributed computing? And how many of you have been working with medical vertical? Okay, pretty much the same people, okay. So, okay, I prepared a little bit more slides than usually, and based on the assessment, I think I will go a little bit more in details about the business case and a little bit less about the technical part. But feel free to contact me and to follow up with different questions, technical one. I have only 25 minutes, so from the moment I consider I start my speech. So today we gather here to learn a little bit about oncology world and how we develop ecosystem or a platform to tie up together multiple roles in a medical system, and even more to do it like a pro with a lot of hashtags in mind, like scaling and switching from CPU processing to GPU processing for training machine learning. So I will skip this one because I don't have time, but everything about this is will be covered in the next 25 minutes. The most part of the business is tied up to the cancer area. So as you may know, most of the cases you end up with tomography or a scan. And in medical terminology, it's we have a dedicated machine. It's called CT scanner. Yeah. So this one, and the patient has kind of a session where it's injected with a contrast solution, and the scanner is just scanning a part of the body. Usually this is very specific and is provided before the session, and you get, just imagine you get a very small slice of you, and for a session you have something between 700 and 800 slices. So this is part of the terminology. So we have a CT scan or a CT session and slices. It's very important to do that because the information you gather from the machine is 2D. And we are going to discuss about how to reshape the entire organ in 3D, and even more to detect any kind of cancer in the organ and so on. Why we do this? Because, for example, there are some organs like pancreas which are behind other organs, and it's a big organ, and you like to be as less invasive as you want in the medical case, and to point to exactly malignant area and try to damage as less as possible. I jump now to an area which is very medical specific, but is very important for our study case. Just imagine that we help a medical, one of the biggest in the United States, clients to automate the entire process in a way that it's very difficult when you have a big amount of data to determine and to contour the organ, and even more to have a good understanding about what is happening. So what you are looking for right seeing right now, it's about a single slice, and specialists, clinicians, are going to paint in different colors different organs. So the main idea is that for each individual 700 slices, a very specialized person will prepare the contour. This is it's a very hard work, but you need this in order to train a machine learning model to identify from a CT scan, from a session, a very specific organ to go forward with investigations. I will escape for a second the presentation to give you a very small, to show you the, 1 second, is perfect. Just to imagine, this is what happened in terms of marking each individual slice. So as you can see, there is a kind of a line, it's black on black, sorry for that. So you just imagine you scan all the body, and for each individual slice, to this slice, you need to put the markers for the organs. It's a tedious work to do this, and especially to cover that part with the clinicians. Medical person with very high skill. The main idea is that we want to build up a model, to train the model, and then to use it as a service. So next time someone send another CT image or a slice to the server, which has an up running model already trained, to receive back maybe only the specific part that you provided. So for the moment, our client has more than 50 different models for different organs, and you can imagine. Okay, let's switch in the presentation. You may imagine how easy it is for a patient sometimes to get the scan and in less than few minutes to have an idea about an organ, if it's affected or not. So what we've done in the machine learning part, we took each slice, and based on the colors that we know, for some sample for small intestine and large intestine, there is a specific color, right? So we took slice by slice, and we created the organ in a 3D way. But this is something that has some tolerance. And in the end, we will identify an organ the way it's right there. So from a 2D information, for a time series, we come up with some kind of this kind of information, which this is called in the machine learning world auto-segmentation. And if you correlate that with the medical, it's organ auto-segmentation. Is it clear? So at least from the business point of view? Okay. The nice part is the fact that there are a lot of, it's a mix of different roles in this solution. And to be more specific, as I told you before, big amount of data, data scientists trying to develop models, and this was done in Python using as a machine learning framework TensorFlow. And as I told you before, the entire solution needs to scale. So we come up with a solution where for getting the data from different clinical sites, which by the way, this company wants to create kind of a portal, and different hospitals all over the world to select from I would say store different models, saying, okay, I want for a pancreas or for liver this model, and I want to use it for next 20 patients. So in the end, it's kind of I would say oncology as a service. You know what I mean? So the main idea is here to bring the data into the system, and just imagine that each individual slice from a CT image session, it's a record into the system. So it's up to the data scientists to gather together all those records for different patients and create a record set. So we group together different records in that somehow match something like patients with same clinical treatment or in same location and so on. And we would like somehow to understand better the record set using creating different types of record sets, like for training, for testing, and for validation. In the end, the biggest problem of a data scientist was, okay, most of the work was not automated. So it was manual work to copy the data from one place to another, to select manually the slices as files in the file system. And even harder to deploy the code for the model into a generic, not scalable platform. And we come up with a concept of an experiment, which is quite trivial in the machine learning world, where you put together different record sets tied up together with a model code, and execute the training, and then deploy the model as a service. But behind the scene, the experiment is only a small part of a big chunk, a big pipeline, a workflow that needs to be executed. And this is the tricky part and the most tedious work for the DevOps, because in the next 5 minutes I will explain you why. The main idea is that, and the main challenge is that everything related to the machine learning part needs to run on GPUs, which, as you may know, they are graphical processor units. They are very smart to compute high amount of operations. It's slightly different than CPU, and the entire process, training process, is CNN, convolutional network networks, neural networks, sorry, and the basic behind the machine learning approach is the fact you can imagine you have a network of nodes, and between the nodes are the weights, and you have to train those weights in a way that at the end you have a prediction, and you operate this kind of train of the network in multiple steps. So it's very demanding. So what we provided as a solution is a combination between CPU and GPU. CPU meaning I need to bring data into the Kubernetes ecosystem, so I don't need the GPU. I can use the GPU, but the GPU is very expensive. So the main idea is how we can have a good mix, a balanced one between CPU and GPU. So let's imagine we have a pipeline which is hosted in a Kubernetes based on the GPU. And this pipeline, from technical point of view, it's built with Kubeflow. Kubeflow is a workflow or a pipeline that runs inside the Kubernetes, can be installed, and to create this kind of pipeline, you use in Python, for example, a DSL. You have third-party libraries to build up this pipeline. The interesting part is the fact that the Kubeflow analyzes each individual node or step in the workflow, and you should perceive this, that for each individual node you have a Docker container which runs in Kubernetes ecosystem. So just imagine, and I will jump on another slide because I want to keep the presentation high level. So just imagine that you have a lot of people in the team. For this particular case, our client has more than 300 data scientists all over the world. And you have to correlate different operations from different people. So every time a data scientist changes the code into a model, this is consolidated in a Git, master of dev. But in the same time, we may have data engineers that prepare new implementation to fetch the data from storage accounts, like Gen 1, Gen 2 generation storage account from Azure or S3 in Amazon and so on. The main idea is that every time someone commit the code and integration testing is passed, and this is valid and monitorized by, in our case, there were 3 different options. It was initially Azure DevOps, since the entire platform is Azure-centric, but in the same time, Kubernetes help us to make it neutral by the cloud provider. And then we switched to TeamCity. Also, few parts we had it in Jenkins, but we reintegrate that everything in TeamCity. So those tools are just watching the commits right here, and for each individual element or change like this, build up a Docker image. So the entire code provided by the data scientist will be packed into Docker image, and will be pushed, in our case, in Azure Container Registry, which is nothing less than the equivalent of a public hub, Docker hub. So each individual input will create a different container, and each container will be recorded right here. Between the registry container and the endpoint of delivery in production or Kubernetes, we have in the middle Helm and Cassandra, which are very useful tools. I would say that past the greenfield period, you may consider that mature tools to deploy exactly the same container in production once it was validated in dev and QA. And this is the beauty of that. Everything, yes, please. Yeah, everything it's automated, and it's very easy to change the container version into production, since Kubernetes lets you scale the instances for each individual container. As you can see here, there are 2 kinds of activities: user activity, system activity. So in red, those are human being. This is a human being action, and everything is system activity. Okay, getting back to the discussion. So this is the pipeline to resume. Each individual step is just executing a Docker, as I shown you before. And for the case of the train, and this is the interesting part, when the execution of the pipeline reached the train, machine learning train, we create a new node in Kubernetes, which is GPU centric, deploy through the affinity the Docker image, train the model out there, and we'll see what is going to happen. Once the training is performed right here, then we should be ready for usage to predict different things. This is a slightly different projection of the solution, and as you may see, there are different clusters for CPU and GPU. This is one solution. You can integrate different services on top of CPU. In our case, it was data catalog. It's a metadata system which stores all the information through the pipeline execution, but also outputs from the training. So just imagine that all those containers, including monitoring, are hosted in a CPU cluster, and everything related to the kubeflow, in particular the machine learning part, is right here. The nice part is the fact that you can train more than 50 models in the same time, meaning for each individual execution of the pipeline, you have an experiment, and for each individual experiment, you can create new nodes, GPU nodes in the cluster to train the model. And this is the beauty of the solution, because you can scale without thinking in any kind of limitation. And this is one of the most hard things to provide as solution, because this kind of solution doesn't exist in this moment. So there are big players like IBM, including the ML part from Azure, but they are not tied up together to a vertical like medical one. So the training is performed right here. In all this time, logs and metrics are provided through the TensorFlow framework, and at the end of the training, the binary version of the model is serialized here in the BLOB files. During the execution of the training, we can take insights about the boarding. Boarding, I will show you in detail what it's all about. This is a very efficient tool for a data scientist who has a good understanding about the dynamics of the training, how good it is. So there are different machine learning indicators for a data scientist that should be taken in account. And in the end, if the data scientist is just saying, okay, this is a good model, it's better than previous, has the opportunity to deploy the model in a service concept, or as called TensorFlow serving. So I will skip this one. This one is the second solution. Azure just announced the preview of support of Kubernetes heterogeneous clusters, meaning you can have one single cluster, not two, as shown before. You have one single Kubernetes cluster, and you have the concept of the node pools. You have node pools for the CPU, not for GPU. So you will end up having all those containers in only one Kubernetes instance, but each one has affinity for CPU and GPU. It's a preview, has been tested by our DevOps team, is working, and the GA is something in the middle of the summer. But it's a very good alternative, and this is very important to have a common and unified way of doing things. This is the training, again, everything executed in Docker container. In our case, as I told you, it's a CNN, convolutional neural network. It's a V1. This is not from the client. I'm not allowed, but the concept is the same. Just imagine that once we have, let's suppose that we have already the organ, 3D organ. And what is doing this is just getting a cube of few millimeters, imagine that, and that cube, it's a reference cube that shows kind of a maligna, or in the other words, cancer. So you move this cube from entire organ, horizontally, vertically, and in the third dimension, in the depth, and you have to reduce the information in such a way that in the end, you create equivalent or kind of a filter applied to the organ to identify the cancer areas. So once you identify that, you need to after the downscale you need to upscale. It's a very interesting approach, and this is very useful for medical persons. And this is happening in trainings. And also in the training, you can see here that you all the time get information about GPU, how many GPUs, how much memory is for that GPU in particular. During this time, data scientists, and for example, this week we've been running auto-segmentation for an organ that was liver, and the liver model. Training for the liver model ran for 40 hours. So you may imagine that is very important for a data scientist to understand which way the model goes. And this is the boarding part from TensorFlow. This one again is created by us on the fly. It's just connected to the training, the output of the training, the logs and the metrics. And you can see you can have multiple already build-up models, or the model that you just want to follow up. And you have mean absolute error or square mean error. Everything that data science needs to have, it has it without the need of changing different things. The last part, and I will end up with this presentation, is the serving part. So let's suppose we have a model is trained, everyone is happy with the model, so we need to go public, something like this. So again, using a server provided by TensorFlow, which doesn't need to run on GPU anymore. This is very important. You just consume, and this is the API from TensorFlow. You just refer into a post request the model, in my case, liver version, I don't know, 12 version of the model, and what do I need? A prediction, classifier, regression, things like that. So I'm just preparing a new image, a 2D image, that I want to send to the train model and to get the contour of my organ, one or multiple organs. So behind the scene is just load the value of the image as a binary one, convert it to base 64, put it in the REST into a REST post request. This is kind of pseudocode in Python. And from the response, you get the prediction and re-convert the bytes into a PNG image file type, and that's all. This slide has already been presented, and I think I'm fine with the presentation. I'm done with. I have few extra slides. I'm waiting and checking your questions. Maybe I can use those slides. I don't know. We'll see.
Thank you.